Hello back. It is time to talk about the Wohl degradation. Alright, so Alfred Wohl, although technically probably his name is more like Alfred Wohl, because he was a German chemist, as many of this particular century. Basically, he came up with a synthesis, or rather a treatment, that would allow a chemist to technically take any sugar and be able to shorten it by 1 carbon, you know, altogether. So in this case, cellulose that has 5 carbons in a chain, with the particular synthesis I'm about to show you, the ultimate end result is that we could take this 5 carbon chain and drop it down to a 4 carbon chain. The way that this works out is that we treat the aldose sugar with amino alcohol, or hydroxyamine as is often known, and you do this in slightly acidic medium. This allows you to get an oxime. This particular moiety is called an oxime once it's bound to that carbonyl carbon. This is then treated with acetic anhydride to ultimately turn that entire fragment up there into a nitrile. And then the last thing is to treat this with slightly strong base, sodium methoxide, to deprotonate the alcohol in pink and kick off the cyano group. The end result is that yes, you are basically removing position 1 entirely from the sugar, while keeping the rest of the positions below what used to be, your bigger aldose sugar intact. This is a method that has been revamped over the centuries, the decades, if you will. But it is one of the methods by which chemists of this era, before spectroscopy, before NMR, figure out what kind of sugars they actually had. They will kind of backtrack it all the way back to glyceraldehyde and see if they had the D version of it, the L version, but then they will able to also determine, okay, so now if this sugar, that we're getting is lysose, then I probably started with xylose, or potentially or potentially the derivative that would also rise from it. So it has a lot of historical connotations. So the way that this first works out is that you protonate that carbonyl oxygen, as you often do, right? So attack the proton, kick off that leaving group, protonate that aldehyde. And once that aldehyde is protonated, your carbonyl carbon is now activated to nucleophilic attack by hydroxylamine. So hydroxylamine attacks that carbon, kicks away the electrons back to oxygen, and you produce the protonated version of this oxime moiety. Alright, so then technically the solvent will get involved here, but I'm going to do it in one step. You do a proton shuffle. You have the proton from the oxime dunk onto the hydroxyl of carbon 1, and in essence you end up forming water as a leaving group. So once this happens, the freshly formed lone pair on your oxime simply serves the role of a base. It attacks the carbon to which is bound to form a double bond, and in the process you kick water out of here. So you make this iminium oxime, I guess technically an oximium moiety, or intermediate. And then what happens here is that the way that this is technically assembled, right? You have an acidic proton, and now that water is going to come in, remove that proton for your nitrogen, make this neutral, kick the electrons back to nitrogen, right? So you have that oxime, portion or functionality, reform right at this step. All right, so this is the end of the first step, or the first reaction sequence. Once you get to this point, what follows is that now you treat this with acetic anhydride. So this will be a separate reaction, but the second reaction in the series. So acetic anhydride basically reacts with the oxygen of oxime. So you have that oxygen attacking one of the carbonyls. The electrons go back to oxygen. In your addition step, you form this intermediate. And then, technically speaking, for the anhydrides, the component right here, which is a carboxylate, that's a fair leaving group. So what's going to happen now is that this oxide that we had generated upon the oxime attack is simply going to have its lone pair of electrons come back down, reform the carbonyl, um, but it's going to do it in a pretty interesting fashion. So notice here I'm attacking the oxime proton, right? So I'm basically shuffling that around because I'm trying to make this neutral. So the electrons will go back to oxygen. Okay, so now that we have this intermediate, now we're going to do what I was implying before. So here we'll have the oxygen come back down. It will kick out your acetate as a leaving group. And this will ultimately generate protonated carboxylic acids, if you will. But it's not a typical carboxylic acid or a typical ester in this case, because this oxygen is bound to nitrogen. So this makes it a little more reactive. Reactive enough that your acetate that you've just generated in this step simply attacks the proton that's bound to the oxime moiety. And then that set of electrons simply moves over to the nitrogen, and over here all that happens is that that nitrogen oxygen bond is broken. It's not as strong as you would think because of the electron repulsion of all the lone pairs present on nitrogen and oxygen. So those that pair of electrons from the NO bond relocate over to the carbon next door, and then these final electrons move over to the final oxonium cation to technically form a nitrile, right? When you take those two electrons and move on to nitrogen, you turn that double bond into a triple bond. But also, the relocation of electrons that you see here in that cascade of electron movement simply forms an equivalent of acetic acid. And the deprotonation right here also produces a second equivalent of acetic acid. So that's what I'm showing you right here. That's how the two acetic acids get formed in this process. And that completes the second step of this degradation. The last step is once you get to this cyano derivative, you react this with sodium methoxide. And what happens right here is that the nitrile component is, a fair electron withdrawing group. And the oxygen bound to, hydrogen makes that hydrogen also relatively acidic, right? So these two combinations make this proton, a prime suspect for an acid-base reaction. So the methoxide literally does that. It attacks that proton. And here the electrons don't just go back to the oxygen. They go back onto the carbon to which that oxygen is bound. And the cyano group is technically derived from a weak acid, which is not the best leaving group, but it's also not terrible. You're not really kicking out a strong base. But this is one of the rare instances where you actually get to break a carbon-carbon bond, right? And it's kind of driven by the fact that the solution is done and the material is reacted under relatively strong basic conditions. So this is not completely far-fetched, especially considering the things we've seen with esters, the things we've seen with, enolates and alpha chemistry, right? Alpha carbonyl chemistry. So, okay, so get back to the point here. Methoxide attacks the proton, the electrons go back to the carbon, and your cyano group, it's kicked off as a leaving group, basically forming sodium cyanide, methanol in the process, and ultimately turning that carbohydrate at position 2 into an aldehyde. So you basically have shortened the chain. This will happen for any of the aldose sugars, right? So you could go from a 6 carbon member sugar down to a 5-member carbon sugar. You can take that 5-member carbon sugar down to a 4-carbon sugar, and from the 4-carbon sugar you can go all the way down to glyceraldehyde. So this method is very convenient because sequentially you can degrade the sugar 1 carbon at a time, and that's the power of this Wohl degradation. Okay, but with all that said, we are done with all the reactions. Not trying to say that it wasn't a good quantity of information. It certainly was, but that kind of concludes that part of the discussion. So now we're going to just talk about what happens when monomeric carbohydrates, monomeric aldose sugars or keto sugars come together to make dimers or polymers. So see you in the next video for that discussion.